Correct?
Yes, sir.
Good. Good afternoon, all of you. Am I audible?
Yes, yes, sir, you are audible.
Okay, okay. So, welcome to the second session of the day 6. So, we have a speaker today, Nidhi Sinha. So, Nidhi Sinha is a research scholar in Electronics and Communication Department at MNIT, Jaipur, Rajasthan, and has done her thesis in the field of early detection and causes of the cardiovascular disease failure using machine learning and AI. She has received a bachelor degree in Electronics and Communication Engineering and Masters in VLSI. She has also done her master thesis on PIN junction solar cell design. She has taught in MTech at the university and also received the Best Thesis Award along with the cash prize. In addition, she has given a selected for the DST Inspire Fellowship provisionally. She has qualified for the GATE 2014 and NET Assistant Professor 2019. She received a CSIR foreign travel grant to attend and present her research at TenCon 2023. She works as a software engineer at Knowledge.ai Nagpur. Currently, she is working remotely as head of AI and at Dynamo 8 Carmel, Indiana, US. She has experience in machine learning and artificial intelligence project development and deployment, as well as in the field of solar cell design. She has published research papers in peer-reviewed international journals and conferences. So thank you, Nidhi, for accepting our invitation. It is now over to you.
Thank you, sir.
You can share your screen.
Yes, a very good afternoon to all of you. And thank you to Amit Joshi, sir, for giving me this opportunity to share my knowledge related to digital twin with all of you here. I am sharing my screen. Is it visible to all of you? Please confirm.
Yes, Nidhi, it is visible. Yes.
Okay, so today the topic is digital twin for AI. So the first question arises, what is digital twin? Uh, it's a buzzword like people are using, but not everyone has the exact idea what it is. So digital twin is a replica of a system, or it could be a replica of a process or physical object, and that is regularly fed on the real data that is coming from that physical system or that physical object. It is dynamic. It's a virtual model, and using which you can see the physical system or object that's sometimes not possible to look inside, or sometime you can monitor it from remote locations also. It is just not a model or a simulation. It's more than just a static copy of an object or a process. It's a dynamic. That means it continuously update on the sensor data that is coming from that physical system. So, overall, the digital twin combines three main components. The first component is the entity. Entity could be a machine, it could be a building, process, city, or a human organ system, of which uh, you can create digital twin. The second component is data connection. Data connection include all the sensors from which the data will be received. It may be IoT devices, telemetry feed, or some of the demographic features also. And sometimes there's a feedback between the data coming and the command or action going back to that physical entity. Now the question is how it's different from the prototype and the simulation. So the prototype is actually a physical or a software early version of any product or a system that is used to test the idea or the concept or form or a function or its usability before full scale production. So prototype is made before a system is actually developed. So it helps to find flaws in the design, or it gathers the feedback. So it's helpful in the development process. On the other hand side, there is simulation. Simulation is a virtual model where you digitally represent a system, where you simulate the behavior in an artificially or stimulated condition. You give a particular condition and for which you see the result, the simulation. Now, digital twin is a dynamic virtual replica, means it's not early version. The physical object or the physical entity is existing, and from that physical entity, data is coming, and that is called physical twin. Then it is connected in real time. Data can flow both way, and it comprises sensor IoTs, as I said before. So actually it is a mirror of real physical object or a process or a system. So next, what are the types of digital twin? So depends on the functionality or purpose for which digital twin is being used. It may be of descriptive, diagnostic. There are some more types I will discuss on the next slide. Descriptive or passive digital twin, what it does, it mirrors the current state of a physical object, and it is mainly used for monitoring purpose or only for visualization. Let's say a car is a covered by tin from the outer side, and if we want to see what is inside just for monitoring how the engine is working, how motor is moving or not, then a physical replica is created, and that's a kind of descriptive only. There's no action being taken. Second is the diagnostic digital twin. It helps to identify problem and deviation in a real system. So how it works, like you design the physical system, you receive the data, and you have a model or ideal case scenario, and then you study if there is any deviation from that ideal behavior. So this is used for diagnostic purpose. That is why it is called diagnostic digital twin. Next is the predictive digital twin. Here comes the role of artificial intelligence in digital twin. Here you not only model the physical entity and monitor, but you can also apply the artificial intelligence or the forecasting models to predict the future behavior or future failure of that system or that process or a machine. For an example, predicting the remaining useful life of a turbine, or predicting the remaining life of the batteries in the car or in any automobile. Next is prescriptive digital twin. Now here it's one step more advanced. You create the replica, you monitor it, and you can also take the corrective actions with the AI optimized decision making, because with the capability of AI, all the data that is coming from sensors uh, can be processed, and those data can be used for forecasting or prediction or both. So here you predict what may happen and then you take corrective actions. Just for an example, in a thermal power plant, you are monitoring a turbine temperature. And based on the pattern, you can predict that in next 30 hours, it will exceed the threshold temperature, and that's dangerous. What corrective action can be taken? You may stop the process for a while, or you may increase the amount of coolant in the pipes. So that's the prescriptive digital twin. One other example is recommending the preventive maintenance scheduled for machinery. Or like in vehicle, you can tell the car battery remaining life is only like 20 days, and you send a notification to the garage where vehicle goes. Like I'm taking a commercial case, not for the personal vehicle, and then it's being replaced. Next type, that's the fifth type of digital twin based on the functionality, is autonomous or cognitive digital twin. So this type of digital twin is capable of self-optimization and decision making without any human intervention. Here, the advanced AI, like reinforcement learning or a general AI concept, can be applied on edge server. Example, a smart factory where robots self-adjust their operations. It was based on the functionality. Next is if we talk about based on fidelity, how many types it can be, like the level of detailing that's captured in the digital twin. So this categorization is done on how precisely the replica of the physical entity is created. So first type is low fidelity digital twin, where you just make the basic representation and you focus on only key matrices or parameters. And it's less computationally intensive. I'll take a example from a human body. Like I have uh, created a digital twin of heart conduction system. That is just one system within the heart, not the whole system. So that kind of digital twin is called low fidelity digital twin, where you only represent or focus on the matrix or the process that is of your interest. You do not include each and every parameter. Another example is the digital twin of a building showing only energy consumption, not the other features. Then the second type is high fidelity digital twin. It has highly detailed, simulates physical behavior accurately. It's extensively being used in automotive industry or aircraft industry where they like test the system extensively before deploying it in the field. Aerospace digital twin is also one example of high fidelity digital twin. Uh, Next is based on the target object. Like what is the target or what's the objective behind creating the digital twin? So it depends on the way you are creating the replica. What's the method of creating the replica? So one is the component level digital twin, where each part of the system is replicated. Like you create a digital twin of pump or motor in a plant. Another is a system level digital twin, where you represent the entire system or the assembly of all the component instead of just replicating one motor from the system, you replicate the whole system. Next is a process digital twin, where instead of replicating a object, you replicate a process. For an example, there is a pumping system in a heart that's pressure regulated. Like if the blood fills in atrium and there is enough pressure, valve open and it goes to ventricles. So it's a pressure. So instead of creating the atrium or ventricle like a physical replica of heart, if you just create this process as a system, then that's called process digital twin. Another example from the industry can be manufacturing process digital twin simulating workflow and efficiency. Fourth type in this category is product digital twin. It simulates the behavior of product throughout its life cycle. Like having a digital twin of a car predicting performance and wear over the time, and you estimate the ideal lifetime will be 15 years or 10 years for this hardware product. It could be a car, it could be any other product. Fifth type in this category is human digital twin. It represents physiology or behavior of human, like patient specific treatment planning. A same drug is given to let's say n number of patients, but the response of the drug will not be same in each of the patient's body. So if you are replicating or modeling that process, that's called a human digital twin, where you're modeling a human behavior that varies from one human to another, subjected on the same condition. And the fourth categorization is based on the integration, like how the digital twin is integrated. One is the standalone digital twin, where you created replica, but it is not fully connected to the actual physical entity, and you just analyze with the help of that digital twin. That's called standalone. Another is the integrated. Integrated means you created a replica, and that replica is connected to the actual object in real time. It's receiving, transferring information to each other. So that's called integrated digital twin. Any questions so far? Sir, can the participant talk or they can only type the questions in the chat? Let me check the chat. I hope I am audible to everyone. Okay. Now I will revisit this role of AI in digital twin. How artificial intelligence is contributing in today's digital twin technology. With the help of artificial intelligence, the data processing is possible and a huge amount of data can be processed in real time. Forecasting can be done to predict the future behavior of the physical entity. Corrective action can be taken because of the existence of the IoT or IoMT system. Machine learning algorithms can also detect anomalies if there is a behavior from the standard behavior of that physical entity. AI model can also simulate complex scenarios with the help of the data coming from physical entity and optimize the process without any human intervention. And especially the generative AI can automate the creation and adaptation of digital twin model for diverse application. Now, the key application of digital twin. So, first is in healthcare industry. As I said before, in healthcare industry, the organs like heart allow AI enabled personalized treatment. You must have seen like sci-fi movies where doctors are zooming in into one organ and see if there is any problem. That may be true in near future with the help of this digital twin technology. A patient-specific AI-augmented virtual heart offer a potential transform medical care by enabling personalized diagnostic treatments, simulating and predicting how the heart will respond to the various interventions. Or what could be the optimized therapy strategy tailored for individuals' anatomy and physiology, so that the risk can be reduced and we can improve the clinical outcomes. Okay. Next application is automotive and autonomous vehicle. Testing and refining vehicles' behavior with digital twin, improving safety, improving predictive maintenance, and today like self-driving cars. Then in the manufacturing, real-time digital twin of production line for predictive maintenance. It can forecast the logistics load, defect the inspection using AI-driven simulations. There is a huge role in smart cities, of course, where AI can be integrated with digital twin to support the urban planning, traffic management, resource allocation. I'm not sure about India, but in US there is an project. A lot of companies there are working upon is intersection. There they are trying to manage the traffic light in a such a way where first responders like ambulance, firefighters, does not have any red light going to the destination. So all the traffic lights should be managed in a way where it turns green when the first responders moving through a particular route. So it's a government project also there. So that's also part of a smart city. Next is the retail. One example is Lois store. It's an American store. It used digital twin and AI optimized operation in store logistics. In India also, a lot of stores like DMart also uses the optimal way to place the product so that the sales can be maximized. Before moving to the next slide, steps to build digital twin, I would like to show one of the example that I worked upon or developed in my company. That's a digital twin of a vehicle monitoring system. It was done for advanced fleet management. So I will just show you one part of this product that's called digital twin. So here you see a car moving, right? And this is an example of AI in digital twin. So with the help of the digital twin, the data is coming. This is just for demo purpose. I cannot show the real customer data. I'm not allowed to. This is our demo application. So you see the car moving and you see everything that a driver can see sitting inside the car, and more than that, of course. You can see speed, vehicle type, but here the AI comes into play. Here, the tire pressure and maintaining the right tire pressure plays a huge role in the fuel consumption. If you running a car on a right tire pressure, you can optimize the fuel consumption. For a single vehicle, it may not make sense, but for a large fleet where millions of vehicles are running, even a small improvement saves millions. So here what it does, it predicts the tire pressure in current and what it could be in the next 30 minutes. If it is green, it is fine if you don't take care of it. But when it goes red, you need to go to a gas station and refill your tire. So at the same time, actually it routes you to closest gas station where you can refill your tire with the right amount of pressure. Or in case if the garage, like in few cases, the big organizations like AT&T have their own garage, have the contract with the garage. So this recommendation can directly be sent to the garage, and driver just need to take their vehicles there, and with the automated system they will know what to do or what action to take, and it will be taken. So this is just one example from real industry. Now I'll go back to my presentation. Here it is. Next is to build a digital twin of a heart, or let's say any digital twin. I'll go with the overall process. Step one, define the purpose and scope. What physical entity, process you want to create a digital twin for, and what is your goal or scope? According to that, in step two, acquire the data, or if you are planning to synthesize it, simulate the data. Once you have the data, go to the next step, that's the building the virtual model. You may use any programming language. Python is very famous these days, but you can also create it in MATLAB. After creating the virtual model, you need to do integrate. Now, if you have created a actual physical entity with the sensor, data may coming from that sensor directly, or if you are using a simulated environment, you need to connect your virtual model with that data simulator. The next step, visualize if it's happening correctly, if it is successfully interacting with each other, you are receiving the data as expected, etc. Then validate and test your virtual model. And then you are all set to deploy, monitor, enhance, protect, forecast, whatever is your end goal. I would like to take some question before I move to coding. I will show you some example of basic digital twin. Let me go to the chat. Please confirm if you can hear me, or you have any questions. No questions? Okay. Then I'll move forward. Thank you, Pravesh, for responding. And text to me if my screen is not visible. Okay, it's being shared. I have in total 4 example. So in the first example, this is a digital twin of a physical machine where we are only taking values from temperature sensor, vibration, and if it is running or not. Running is set to true, and then we are monitoring the temperature, as you can see. This is a random system that I am just using to demonstrate how it can be designed in Python. So I have taken some random values for temperature, so for vibration, and uh, I have set up like how vibration will increase in time or temperature. Then this portion is to get readings of temperature vibration from the sensors. And then here it is, the digital twin. So self.physical is equals to physical machine that you have designed. It will gather the latest reading from the top, the temperature and pressure. Then here is about training the dummy model. I'm doing it for the range 1000, and T means temperature range 20 to 40. For vibration, it's 0 to 2. And now if the temperature goes above 30 and if vibration goes greater than 1, you need to append. And then here a classifier logistic regression is applied to these data, X and Y, and then it's updating. Now it will print the status, the temperature and vibration, and it will be predict if there is any fault or probability of fault, I should say. If the temperature is going too high too soon, there is probability that it may catch fire. Likewise. So let me rerun the whole code. One moment. I'm supposed to selecting Python 3.9. For some reason, it's not selecting 3.9. Let me try one more time. Here it is. Okay, let me run this code. It's okay. It already ran actually. It takes only few seconds. Okay. So it's the second example. Here is the first one. It's still running. So as you can see, the output is coming for temperature and vibration and the fault probability if there is any with the help of the model we deployed. It will take some time to run. If you want, I can share this code. You may follow this as a prototype to build your own digital twin of a system. Let me show it to you in the text editor. So that's how the value will keep coming, and that's why it is called real time. This code will not produce the same result every time. The reason is I'm using the random number generator here to for the temperature and vibration values. So sometime like this time you got no fault predictability in any of the case. May if you may run this code 2-3 times, at some instance you will see there is a probability and the fault probability has some number greater than 0. Okay, I'll move to the next example. Let it, okay, it's again with 0 probability. The code is still running. Once it will be completed, I'll move to next. Okay, I can. So let me explain the system a little. This is a system where we are trying to find the error or gap in the actual capacity and the simulated capacity. Sometime maybe in a vehicle or where in logistic market, this can be an use case where you simulate capacity, but actually when it goes into field, the measure capacity is different than what you have simulated. So here you see the data is coming for both simulated capacity and measured capacity. Here it is created two data frames, X in and X out. So X in is the simulated capacity, whereas X out is measured capacity minus simulated capacity. That is the error in the simulated capacity. And here the data is prepared for training and testing. Sequential model, neural network model is deployed with the two layer, as you can see, with the activation function ReLU, and it is compiled with SGD optimizer. It is just for demo purpose here. So you see the outcome just for one iteration. You see the predicted error is 18.445 and the adjusted capacity. Adjusted means the true capacity, okay, apart from the simulation. So that is 130. So this is one of the example of where you want to diagnose how accurate your simulation is for the capacity. I'll move to the third example here, and it is from biomedical. It's a digital twin of a physical patient. As I was talking, so imagine you are creating digital twin of the patients coming to the hospital. You have some values: glucose, insulin, food intake, okay, and glucose in mg per dl. You can also set the units. Now the food intake is random, like glucose and insulin will be coming from some measurement, let's say sensors in this case, and that will depend on the food intake of the patient, what he or she is eating. So food intake is a variable here in time. So that is why it's simulated, let's say, between a given value here with the NumPy library. Now, Glucose level will rise if the food intake will more, as I said, but at the same time, it will not only depend on the food intake, it will also depend on the insulin. So, in a normal patient, no matter what he eats, if he is healthy, insulin comes and it adjusted the glucose level in your blood. But with the aging, when you get diabetes, this insulin secretion gets affected and your glucose level is not being adjusted. But how do you know? Until unless you have some symptoms, you don't know. But with the help of this type of digital twin, that can be achieved. So the function is set in a such a way where food intake, like the glucose level is food intake multiply 0.5. It's purely random. You are advised to take these numbers from the literature or from the previous study, or you can perform your own study to set up these numbers also. Now, for the insulin, it will go subtracted by the factor insulin multiplied by 0.2. So the glucose will be, here I am taking some random uniform number between -2 to 2, and this is the function. So if insulin is less than 0, it will get the reading. Let me show you the digital twin now. So this is three function inside the class biomedical digital twin. Here you have physical patient, you have the latest reading for glucose, insulin, and then you have designed a model here, let's say linear regression you're considering. And then you are recording you're recording the values of glucose, insulin level, food intake. You train a model and then predict the next time after the training. If a person has eaten a plate full of pasta, what would be his glucose level after 2 hours? Okay, so that's what being done here. And here it is to display the output. Now, let's run this code. I already run it, sorry. Let's go to the output now. You can see full output in the text editor here. So you see the glucose level, you see the insulin, food intake is 0. A person will not ideally be eating all the time. So food intake will not come in all of the data point. It should not be there. It will come after an interval. So food intake is 0, model is not being trained here. At this point, you see the food is taken, right? 50.78. And then you record the glucose again. These number will not make sense. I repeat, this is coming from a random data. My intention was to convey how this type of digital twin can be created in Python. So that's how a create that's how you can create a very simple physical patient digital twin to monitor the glucose, and you can train a model on top of it to predict the glucose level based on the food intake. This is actually a great work because everyone knows how the diabetes has been a big problem and it's incurable. It can be controlled if you are pre-diabetic, or if it can be detected at a very early stage. You can take some precautions. But even with that, you don't know what to eat, what not to eat. Everyone doesn't have a calorie meter in the brain. This has glucose, fructose, or protein, carbohydrate. So if this can convert it into a product, imagine, that captures the picture of food, estimates the weight of the food and type, and based on that, it gives you the nutrients amount, and it advise you, no, you should not take full plate. You may eat it, but only eat half of the plate. That kind of thing can be done. Now I'll move to my fourth example. And here, as I explained, when you are not using a real physical system, you need to generate data with the help of a data generator. And this is a digital twin of human heart. I'll add that. So human heart. So here I'm taking simulated data for age, blood pressure, and the heart rate. Only three parameters. And then here the QRS. QRS is feature characteristics of the ECG signal that is created here, modeled here. And then the health status. If the heart rate is greater than 90 and at the same time blood pressure is also greater than 140, it means you have some issues, right? It may be temporary also. Now here the heart rate is being simulated. You have collected features as age, BP, and HR. You created X train and Y train. Y is the QRS interval of ECG signal. Here it is. So this QRS is the Y and this data you are getting from here is the X. And then you define a model, and it's a regression model because QRS value is not a category. It will have a continuous number. So, and after defining the regressor here, now let's take a new patient whose age is 60, blood pressure is 130, and heart rate is 75. Okay, now you will know the QRS without performing an ECG test on that person. That is one application of this code actually. Let me run this code. And QRS threshold is set to 120 further for the classification. So if it is greater than the threshold value, like if it exceeds 120, it means you have possible arrhythmia, either arrhythmia or you have conduction block, right? Else your heart is functioning normally. Let the code run. So because it will give you one result, because here you are defining only one new patient. So instead of defining it for one patient, you may define it for multiple at a time for testing purpose. So new patient's QRS value is 76.49 and the normal heart function is predicted. Run it one more time. Now QRS is 80 and again normal. You may run this again and again. It will give you the random values. Okay. So this was all about the coding, and in the last 10 minutes, I would like to take questions. Any questions so far? Okay, you can reach me out if you have any question, even at the later time. Uh, if you don't have any question, I will elaborate on one more digital twin that I mentioned during my presentation. That was of the digital twin of conduction system of human heart. So this is a roughly drawn diagram of heart conduction system. It has four main points. First is the sinoatrial node, that's SA node. An electrical impulse is generated from here, SA node. And through the internodal pathways, it goes to AV node, that's called atrioventricle node. From there, it goes to bundle of His. Bundle of His is divided into two parts, right bundle branch and left bundle branch. And there is a small fibers known as Purkinje fibers. So there are different stages of the heart block. Like in the type 1, there is a minor blockage, let's say in the Purkinje fiber, electrical impulse is not traveling. You will not have any direct symptoms there. You will feel it only when it goes to type 2. Then you will have some symptoms like fatigue. And in type 3, like AV nodes pick up, like generate, but in a complete heart block, heart failure. Either SA node is not capable of generating the impulse, or the impulse generated by SA node does not able to move to AV node. So for it, first you need to design a digital twin system. Here it is designed with oscillators, of course. So one block for SA node, one for AV node, one for his Purkinje equivalent, like for the fibers. Now at the SA node, a heart rate variability is included, because this impulse, like if you're running, there will be more like fast response generated at the SA node. Then from this, the waves, P wave, T wave, QRS wave, like it's being generated at the same time in a real system. Some noise is being added, and the respiration that you take, it's also considered there. And there you have a final ECG signal. But that signal is coming from digital twin that I simulated. Next step, you are recording these signals. Now, there could be two application. One, you can only use it to monitor, like you integrate this with the actual values of SA node and AV node values, and you just monitor the ECG signal. But the work I have presented was for prediction of the diseases for which the data is not available. One of the major issues students face in who are working in the biomedical is the availability of the data. It is very limited, and if you want to collect it from the real subject, you need to get that subject sign the consent form. You need approval from ethical committee. In few countries, privacy laws are also concerned. You need to do certifications like HIPAA if you want to work on any biomedical systems. So, this type of technology can simulate the ECG data for certain abnormalities. As I said, type 1, type 2, type 3 block. And what happens, that is kind of predefined. 1 out of 10 P wave, you will have a lesser amplitude, and that indicates toward abnormality in the conduction system. So, what will happen? You can collect the sample and you can train a model, like a pre-trained model. And then, if you will use that pre-trained model to a real subject ECG, that model will be capable of predicting the disease, predicting the presence of a particular disease for which you didn't have the actual data. Number two, it will also be useful in continuous measurement of a patient in a real time in an IOMT network. Idea here is drawn, like if here is a subject and ECG may be acquired from smartwatch, maybe Holter monitor, and that ECG goes to patient specific digital twin that is on the cloud, and there you apply model. You merge this ECG with the patient record. If it has any history of diabetes, if he's a hypertensive, if he has any heart problem or cardiac arrest in the past, and you combine all these data and then you subject it to an AI model that predicts if the patient is healthy now, or it has some issues. If it has some issue that needs immediate attention, it will raise a notification to the mobile phone, as well as he'll send notify the healthcare provider, that may be a hospital here, to take action so that life can be saved. So that is all from my side. Thank you again, and once again, I welcome any question if there is any. Was it now knowledgeable? Like, have you learned anything? Okay, thank you, Akash. Thank you for responding. Thank you, Sana. At least it assures that you were listening. Thank you, Vibhuti. You can write me an email if you have any questions related to this, and the presentation and the content will be shared with all of you. Thank you, Seema. Thank you very much. Thank you, all of you. Have a great day and a nice weekend. Okay, this is the last session. So you, all of you, may leave the meeting, leave the webinar. Thanks once again to all of you. Bye.